Okay, let's continue our discussion on introduction to algorithms for data mining and machine learning. In this section, we are focusing on data fitting and regression. So by now you understand what is algorithm, what is optimization, mathematical foundations, and also in-depth understanding of machine optimization algorithms. Finally, at least as a start, we started talking about some machine learning algorithm, and then from here, you would see the connection between all these algorithms together with optimization algorithms. Okay, sample mean and variance. For a given set of independent sample observations x1 to xn of random variable x, capitalized X, the sample mean is nothing but 1 over n sum up all the individual observations and divided by n, right? So that is the mean, which essentially is the arithmetic average of the values of xi. And then the sample variance is 1 over n minus 1 sum of xi minus x bar squared, sum of them up. It's worth pointing out that the factor is 1 over n minus 1, not 1 over n, just because of the we lost 1 degree of freedom when you calculate x bar. So in order to design a matrix that is unbiased estimator of the population variance, we leverage this 1 over n minus 1. You have to, if you think about this, right, we discussed the mean and variance earlier as well, but here we're talking about sample mean and sample variance. Let's use this example to understand it a little bit more. We know the measurement of quantity for noise level would be all of these observations, 66, 73, etc. And now we have 10 observations. We can calculate the mean by 1 over 10, sum all of these observations up, and then you get 73.2. And you can use similar methodology to calculate the sample variance. S squared equal to 1 over n minus 1, sum these quantity up, and then you can get the sample variance, variance being 21.73. And then the standard deviation of this sample variance would be square root of this quantity, which is square root of 21.73 equal to 4.662. By now, I'm not sure if you actually have any exposure to regression. I assume you probably have already. If not, there will be specific courses that focus a lot on the regression theory in this curriculum. But here, serving as an introduction and a demonstration of the relationship between regression and optimization, we started the discussion on regression. The regression idea is to fit the data points xi and yi. You see that xi, yi stands for a specific data point. For example, this one point on the chart, blue point, would have a specific xi and yi coordinates. So now we have a bunch of observations that's represented by this blue dotted observations. Then what we're trying to do is we come back with a function y, which is fx. In this particular case, this red line is y equal to a plus bx to fit these observations. Question is, how can we find the best fit? what we're really trying to do is trying to find the best fit that minimize the sum squares of errors, which is corresponding yi minus the predicted value from this line of fxi. So let me use some sort of line. Okay. So essentially, for each observation, we would have a corresponding predicted value for y, right? So that would be fxi. This would be fxi, and then we have yi. The distance between them would be this, right? This is the distance between yi and fxi. And then we use this particular quantity, we call it as error term. It's also called as residual. And then once you, what we were trying to do is really trying to minimize the sum of all the sum of the squares for all the error terms, all the errors. This is basically a vertical line that's parallel to y-axis. Yeah, this one is essentially on the line, which is 0, right? So all of them. We're really trying to minimize the sum of squares of errors. Again, if you think about it, if I have a separate line, which is shown here as a yellow line, that's potentially another estimation of our function. But we would know we're trying to find the minimized sum of squares, which is a red line instead of yellow, because the yellow would come back with a higher sum of squares of the error. Okay? That's why we call this approach as method of least squares. Okay, this is a simple linear model, meaning we only have one independent variable. Okay. If we take a partial order derivative of this quantity C by A and set it to equal to 0, and then take partial order derivative in terms B, set it to 0, then we have this relationship, which can determine A and B uniquely. After some algebra, we have A being this quantity and B being that quantity. So we have an estimate of the A and B. Now, what does this mean? This essentially tells us the linear regression model is an optimization problem, and then it is a quadratic optimization problem. Okay, if you ever heard of regression, you know that we're trying to find the best fit line. But I hope that in a further understanding of the regression line, now you know it's a quadratic function minimization problem, and then we're trying to find A and B so that this sum of squares of errors is minimized. Okay. The correlation coefficient measures the degree of correlation between x and y. That can be calculated through this way. And then it can also be written compactly as this format, which is a bunch of calculation between x and y. Kx is sum of all of the x, and ky is a summation of all the y. kxx is the summation of all the xi squared, kyy is summation of all the yi squared, and then kxy is the summation of x and y. N times kxy minus kxky divided by n times kxx minus kx squared times n times kyy minus ky squared. That is our correlation coefficient. And then the correlation coefficient should be between -1 and +1, because this is essentially a linear correlation coefficient. If it's larger than 0, we call it positive correlation. That is to say, when x increases, y would increase as well. When r equal to 1, it is a perfect increasing linear relationship, meaning x and y have a linear relationship, and then it's increasing. When r is 0, we say it's, or near 0, then we say there is no correlation between y and x. And when r is less than 0, it is negative correlation. Especially when r is -1, it's a perfect decreasing linear relationship. As x increase, y decrease, and follows a linear relationship. So if r is larger than, r absolute value is larger than 1, then there must be some mistake in your calculations. This is identical to when we talk about probability. It should always be between 0 and 1. And then correlation coefficient, it should be always larger than or equal to -1 and less than or equal to 1. For this set of values, you should be able to calculate our to estimate the function itself, best fitted line, by calculating a and b, and following the specific calculation equation that we come back with that follows the optimum solution. And then for this particular one, you will say y is 1.06 plus 0.5x. Similarly, we can come back with the correlation calculation. It turns out to be 0.98976. And now, as an exercise, we want you to use this set of data, try to calculate this y and a and b from this set of equations. Remember that I'm not asking you to use linear model LM in R to fit the regression line. I'm asking you to use this specific linear equations, specific equation set to come back with an estimate on A and B. On top of that, if possible, use linear model if you know LM to fit the line to see how close those two are. Okay, here I introduced you the linear regression. Now, what if some of the model functions look nonlinear? One possibility is you could convert them into linear form. Let's use this as an example. It's a nonlinear function f(x) equal to alpha times e powered by negative beta x. We know if we take a logarithm on both left-hand side and right-hand side, we should come back with log f(x) equal to log alpha minus bx. And log e is 1. That's why we have minus bx. Now you can see that if we use y stands for log f(x), a is log alpha, and b is negative beta, then we can translate this original problem to a linear function form. So we could estimate a function. Once we estimate, come back with A and B, we translate back, we should be able to come back with an estimation of alpha and beta. For the following function, that is fx equal to alpha times x powered by beta, it can also be transformed into log fx equal to log alpha plus beta log x, which becomes y equal to a plus bv. Y is log fx, v is log x, and a equal to log alpha, and b equal to beta. So that's another transformation. Similarly, for this relationship, you can do y divided by x and then takes a log. This is another one. So once you know your x and y, you can always use a transformed format to calculate the slope and coefficient, slope and intercept for the linear regression line. And then we say that log y over x has a linear relationship to x. And then here, log fx has a linear relationship to log x. Basically, I'm saying log y have a linear relationship in terms of log x in this example. So this is called linearization. Let's think about something called generalized linear regression. We're trying to fit a polynomial of degree of p, and then it's the most widely used generalized linear regression model. So this is equivalent to the regression to the linear combination of the basis function of 1, x squared, etc., all the way to x cubed. For a set of data points xi, yi, the minimization of the sum of the error squares leads to this following formulation, which is a matrix equation. In principle, alpha 1 all the way to alpha p can be obtained by inversion through the Gaussian-Newton method. It's more efficient. So let's see what's the construct of this matrix. On the left-hand side, you can see that in terms of the row, the first row is sum of 1, just because we also need this alpha 0 estimate. And then the second element in the first row is sum of all the xi. The third one you can think about would be sum of all the xi squared, sum of the xi cubed, all the way to sum of xi powered by p. That's the first row. And the transform, or if we say that the prime of this row would be identical to the column because it's symmetric. And then let's look at the diagonals. For the diagonals, the second one would be sum of xi squared. The third one would be sum of xi cubed. xi squared. The third one is, I think, right? The last one would be xi 2p. Yeah, basically the last one is xi powered by p squared. And then this one should be xi powered by 2 squared, xi powered by 4, basically, sum. So that is this matrix. And then on the right-hand side, sum of yi, sum of xi times yi, sum of xi cubed, xi squared times yi, sum of xi cubed times yi, all the way to sum of xip times yi. So once we have this formulation, we can use matrix inverse of this matrix, so that we are able to calculate the corresponding of this alphas. So let me use some text here. So I'm saying is m times, let's use let's use alpha. Yeah, let's use a, which is this alpha. M times a equal to, let's use y. So what we can do is we can first thing that what we need to do is we use m inverse. I want to use power, but doesn't look like I'm able to. So let's use inverse. Inverse of m times m. So on both sides, right? From here, we know that it should be equal to what? Inverse m times m is identity matrix equal to a times inverse of m times y. That would be our calculation, so that we know a is inverse of m times y. So we're able to calculate this a, which essentially this column vector, based on the inverse of original matrix times this y. Okay, that's what I want to write. Now we use this simple example to look at quadratic regression. So we have x and y observations. We want to estimate. We want to come back with this formula. Only have three terms: intercept, x, and x squared. Three terms, but two independent variables. One of them is x, the other one is x squared. So now, if you follow the equation, you would be able to calculate all these quantities, and then you would be able to come back by with alpha 0, alpha 1, and alpha 2, and then this is your best fit equation. Now you need to implement this using R or Python and compare the results. So in the homework, I will specifically specify what do I mean by implement. You need to do two things. One thing is to do the calculation through this mathematical way in R. Second way is to use the LM model for linear regression to come back with the estimation of the regression model, and then compare those two. Of course, it should be very close. Even though there's one thing that is, even though there might be some numerical difference, you should be aware there's this possibility. Now, question is, how can we evaluate how good is our estimate? We want to introduce something called goodness of fit. So remember that the data that we had, we fit the data using a p equal to 2 quadratic function. If we plot out the curve, it is well fit just because these are our original observation. This is our best fit, which is a quadratic function. And then we call it, the question is how do we know it is well fit by choosing p equal to 2? Reality is p is a hyperparameter that we can adjust. In machine learning, you would come back with a lot of cases that need to do some sort of research on the hyperparameter. So if hyperparameter is new to you, I just want to introduce what hyperparameter is. It is a parameter that you can adjust so that you can pick the best of all the models that potentially that can fit. That's called hyperparameter. So now we use p equal to 1, 2, 3, 4, so that we have different fit of the functions. For example, when p is 1, we're coming back with this linear line. And then when p is 2, we know we're coming back with this line. When p is 3, which is also red dotted line, which is hard to see, but indeed it's there, right? You saw it. This side is harder to see, but on here you see the difference. Of course, we also have F4, which is not plotted here in this particular graph. Now we could find the fit error, which is residual sum squares. Remember, we have this calculation. We say, okay, what is my yi minus my yi estimate at xi, and then I get the difference and squared, and then sum all of them up. That is our residual sum of squares. For p equal to 1, we found that residual sum square is 36.34. And then p equal to 2, it's this quantity. And then p equal to 3 is this quantity. P equal to 4 is extremely small. Now here you see that I said p equal to 4 leads to overfitting. If you know overfitting, then you know what I'm talking about. If you don't know yet, hold on to that thought. We're going to have more discussion on overfitting very shortly. In other words, we want to minimize this residual sum of squares, but we don't really want to go to some point that is a perfectly fit, almost like every single point fits the curve. Okay, or every single point is on the curve. That's the type of scenario that we really want to avoid. We would have this overfitting discussion shortly, so you can hold on to that thought, and then we can have further discussion right here. So for higher order polynomials tends to overfit the data. The oscillation between issue of and oscillations become an issue for higher p. So RSS is not a good criteria for measuring the goodness of fit. So so here, essentially, I do want to give you an example on overfitting. Let's just use linear regression as some sort of example. Hold on, let me. Again, let's draw some dots, right? Suppose these are all my observation, right? Now, one possible estimation of the linear regression line would be, let me use a different color, would be this. as we know. Let's assume this is our best fitted line. We call it line 1. Line 1, right? And then there's another possibility, right? We instead of using this linear regression, what we can do, we just connect all the dots, and then we can our estimated function is like that. For line 2, multiple segments. For this estimate, we know the residual sum of squares should be 0, right? Because it's a perfect fit. Every single one point is on the line. Lines, right? Line segments. So this one have the RSS being 0. But we're not going to pick the red line segments just because it has overfitting issue. What does it mean by overfitting? Because it fits the data too well, so that if we have a new observation, we are not able to estimate what's the corresponding y. So if suppose that we have a new estimation like this, we have a new estimation of a new observation of x. We don't know the y, right? So let's say that we do have a new estimation that is along this line, along this x. Then it doesn't have a lot of prediction value for the overfitted line, but the original line that we come back with doesn't have this issue. So in other words, it cannot be generalized. So we would have some discussion on the bias and variance. Bias and variance. It's called. Let me get a proper. Is bias and variance trade-off. So you have to think about, we're not trying to find a model that fits the data perfectly. We're finding a model that fits the data reasonably well and it's able to predict what's that you have not observed yet. So that's the point that I'm trying to make. So that's a brief discussion on the overfitting. Now we use other two different metric to measure the goodness of fit. One of them is called AIC. The second one is called BIC. And BIC is Bayesian information criteria, and AIC is archaic information criteria. You would realize that AIC and BIC have some sort of relationship. That's why they're actually somewhat, quantity-wise, they are different, but they are somewhat related just because you are able to represent AIC by BIC or the other way around. So AIC is defined as 2k plus n log RSS divided by n. N is the n data points number of observation, RSS is regression of sum squares, and k is the k parameters to fit the n data points. So for smaller number of samples, for example, n divided by k is less than 40, the corrected AIC becomes just have an extra term that have k and n relationship in there. With the same assumption of error obeying Gaussian distributions, we have BIC definition. K times Ln. So you can see the difference is really on this component. And then both AIC and BIC are useful criteria, and their global minima gives the best fit, best k-value, or best p that we discussed in the previous slide. It's difficult to say which one is better, which may also depend on the types of problems. In other words, sometimes it might give you a conflicting conclusion. If you use AIC or BIC, then you have to figure out if it indeed give you conflicting conclusion, meaning AIC tells you model 5 is better, but BIC is telling you model 8 is better. Then you have to make a decision which one would be the right model to pick. But the majority of the time, they should be consistent. AIC says model 5 is better. BIC also says model 5 is better, or best. Let's put it this way. It should be really the best. We're looking for the best model. Let's revisit this example that we have for 5 data points with polynomials. We have p equal to 1, p equal to 2, p equal to 3 in terms of number of parameters. Because we also have that intercept, it should be p plus 1. So now we have 2 parameters. Again, if you go back to parameters, one parameter would be this, the second one would be that, right? Those would be 2 parameters. For in case of p equal to 2, we have 3 parameters, 1, 2, 3. So now we have 2 parameters, 3 or 4 parameters. We calculate RSS, we calculate AIC, and also we calculate AIC corrected, which have the extra term that we had just now. And then we have BIC. You can see that which one is minimizing AIC and BIC. You would see that p equal to 2 is consistent with AIC or AIC corrected, and also consistent with BIC, which is the minimal. Now we see that we pick the right model based on AIC and BIC. Okay, we just discussed data fitting and regression, and then next thing that we're going to discuss would be nonlinear least squares. So it's a natural stop for us for now. So I'm going to stop here for this lecture. We'll continue with nonlinear least squares next time. Thank you.